Good morning, everyone. Welcome to the EasyPower Tuesday Refresher. You're all welcome to contribute to the discussion by submitting questions or comments during the session, and we'll try to get to them as time permits. And today we're exploring the specific topic of modeling photovoltaic elements in EasyPower. I've got my title slide here indicating 2019. It's not really indicative of changes so much in EasyPower as for my own edification as far as timestamps on when I do this. There are some subtle differences due to the 1584 model as far as the analysis, but modeling is pretty much the same. Welcome all, and as we try to do most sessions, I'd like to start with a poll question to get a little bit of feedback from the audience. And so the first question is, how often do your PV designs include alternate sources of energy? So if you would please kind of contribute to the discussion by indicating what you kind of systems you work with. We appreciate the feedback. It's no obligation or liability, but it does give us some insight into the type of systems that you work on. So we'll give this another 10 seconds. Looks like we have a plurality of people attending, contributing. Thank you very much. So here's how everyone has weighed in on this. Looks like a fairly wide selection of alternatives. And then second, how large are the systems or projects that you usually undertake? So let's see if we can get some feedback on this one. And I'm always impressed with how wide a spectrum that this covers as well when we issue this question. And looks like we're about half of the audience. Let's give it a couple more seconds. We thank you very much for attending today and your support of EasyPower. And here's how people have weighed in on this. So it looks like the majority is, or at least a large minority is the smaller systems. Fair enough. Okay, so let's jump into what we're talking about today. Basically, we're going to talk about some basic elements in a photovoltaic system, how to set them up in EasyPower, and then we're going to run over. So basically, modeling is the focus, but at the last 5 or 10 minutes, we'll be getting into analysis and hopefully some guidance in how to dealing with some of the issues, because there are some differences in the way you look at the world when you're talking about the DC systems. So first of all, probably one of the strengths, as far as I'm concerned, with the EasyPower methodology is the lack of need to deal with the manufacturer's name, serial number, or part number, because as we do in AC elements, we look at the construction and the basic electrical theory, if you will, behind a piece of equipment. So what we do is model the array rather than an individual model or panel. And so consequently, you can take the data sheet and extract the information that you need from the information the manufacturer supplies. And so this would be a typical set of parameters and the definition, as far as EasyPower is concerned, of the different points on a individual array or module or segment. And then based upon what you're trying to accomplish, you can put those elements in parallel to get additional current, or you can put them in series to get additional voltage. And so as you do that, then those data points for the module itself or for the array will be the elements that you enter in EasyPower. So when we come back and define the voltage for maximum power, short circuit current, and the open collector voltage, those are elements that can be derived, as I say, from the data sheet. And then by that definition, EasyPower utilizes this basic model for both max power calculations and in the power flow side of the world. So what an array looks like, the element icon looks like for an array, a photovoltaic array, appears this way on the one-line diagram, and the data dialog box now includes the max power rating, the short circuit current, the open collector voltage, and then the max power voltage. And usually this will be reflected of whether you've stacked up the modules in series or in parallel or a combination of both. So any size array can be accommodated, and it doesn't matter what the manufacturer is or the model number is, as long as you can take that information from the data sheet, you can model the element in EasyPower. Now in a battery, the same type of methodology, we're not talking about part numbers or model numbers or manufacturers, we're talking about the type of battery and effectively the voltage and internal resistance. So if you look at this website, which is a nice reference for information on batteries, you can see the different types of batteries have a characteristic impedance that can be estimated with these levels. So if we were to say we have a acid flooded cell battery that we wanted to characterize, and it was rated for 250 volts, and it had a 200 amp hour rating with 8 hours discharge time, which is roughly 25 amps per hour, then the internal resistance equals the voltage times the per unit impedance divided by the rated amps. So in this case, it'd be 250 volts times 0.1 divided by the 25 amps, and we get a estimated impedance, internal impedance of the battery at 1 ohm. Then we take that information to EasyPower. It's basically the rated voltage, the total impedance, internal impedance, and then the rated amps. Rectifiers, on the other hand, are a little bit different in that they can be either diodes or switched elements. The approximate relation for a diode rectifiers, the DC voltage is approximately 1.35 times the AC voltage. Now, if we had an IGBT element, then there would be a cosine and angle term based upon the firing angle, but the short circuit load at the load side can be as high as the AC short circuit equivalent in amps. Just another side note, in general, the term for rectifiers and inverters is converter, and they're the most common source of harmonics in the power system. So when you get into analyzing the harmonics that are injected, this is a place that you need to verify you have that information in your model, because in terms of converters that can be switched mode, they can have switches in 12, 18, and 6 pulses respectively, and this will generate ripples along with the harmonics. At any rate, the inverter dialog box looks like this, where we have DC and AC coming out. We put the rated kVA. The X over R can be calculated based upon the kVA and the voltage. And then there's a maximum or recommended maximum full load current protection capability. And then the data sheet usually will indicate how long it can survive that kind of a fault. And so this frequently will be the protective mechanism in our system in terms of short circuit time calculations. And likewise, a rectifier, basically you have the rated voltage, the full load DC current, and then the max fault current and the max time that can survive that amount of current. So those are the elements. So let's jump into EasyPower and look at a couple circuits. And I say the nuances here, that modeling is relatively straightforward, and the nuances end up being how we do the analysis and how it's different from an AC system. In our basic installation of EasyPower, under the one-line folder, there's a sample folder, and one of the samples now is included is called photovoltaic.dez, and it looks like this. All right, so our arrays are custom sized, and basically they're able to produce 40 kilowatts with a short circuit rating of 67 amps and an open collector of 660 volts. Max power production is going to be at 600 volts. Everything is protected by a 100 amp fuse, and both at each end of the conductor, and then we have a combiner with an inverter to take the DC current and produce AC that we can put back on the grid. So I'm going to go into short, now that we've got this all drawn up, let me reduce my control box. Go into short circuit focus, fault all the buses, half cycle current. Now, half cycle current, basically, there's no such thing as half cycle, 5 cycle, and 30 cycle. It's all going to be the DC level, and there's no particular phase difference. But what we see is a production of 67 amps from each of the arrays for a total current on the combiner bus of 530 amps. Now, the difficulty that this presents is that this current level, this is the short circuit, the initial fault short circuit current, is not that different from the power flow current, the normal operating quiescent current. If we go into power flow and solve the equations, we see that we have 40 amps. I'm in power flow analysis right now. I'm going to go look at my power flow options, one line output, and my branch flows. Let's look at current and amps. So we have 67 amps, which is the maximum current out of each of the arrays, and it's very close to being exactly the same as the short circuit current. So the difficulty that presents then is how we protect workers that need to work on this bus while it's hot, if that is the case. So I'm going to go back to short circuit focus, fault all the buses, and when we go to Arc Flash, we see we have instant energy of a little over 4 calories, 4.5 calories. If we look at our range for Arc Flash and fault an individual bus, we see that the maxed bolted fault current is 500 amps, and the maximum arcing fault current, which is roughly 50%, is going to be 260 amps. Now, there's not a DC model in the IEEE standard for Arc Flash calculations. There's not a model for DC. The analysis that EasyPower uses is referred to as a max power method, and that's fairly straightforward, and it's actually well documented in the help manual. But in essence, it's at the point where we have 50% of the maximum current supplied to the DC bus. Now, the thing that you'll see here is that we've limited the calculations times to 2 seconds, because in reality, the fuse will not trip at the fault current that's being calculated. So if we come up and look at our short circuit options, I didn't mention it, but basically the same modules that we use for AC Arc Flash calculations are used for DC and Arc Flash, short circuit and Arc Flash. So I'm looking at the latest model, 2018, we're excluding the main, and we've limited our calculation times to 2 seconds. If we look at this, we can see that there's basically no trip time, because at that current, this fuse, either fuse, will trip. So the calculations is basically based on the manual time, which is 2 seconds, and that's what's given us the 4 calories, 4.6 calories. Now, the thing I wanted, and let's go ahead and fault the AC bus, and there we get slightly greater, and again we have the manual time from the DC side, and we have FS6, which is our primary fuse on the AC side. So that is pretty straightforward. Couple things before I leave this particular example. Another strength of EasyPower, when I'm in database edit and I've mastered or completed a configuration that I like in particular, I can save that configuration as a subsystem, and by doing so, I can then produce or repeat the design by going to Insert, Subsystem, and then pick from that subsystem things like a wind farm that I've built up previously and combine that with other PV elements and be able to, in very short order, produce a farm that's just a combination of these elements, and they're all already pre-sized, and I know their short circuit functions or parameters based upon having saved that as part of my preliminary system. So that's called subsystems, and to do it real quickly, if I go back to database edit, I'm in home, I come up here and start a new subsystem template, and from there I can copy any system element or combinations of a design and paste it into the new template. Save this now with a spiffy name that identifies what it reflects, and it will be in my subsystem folder for future reference. All right, that's just an aside. I want to jump out of this and look at a little bit more of the tricky side of doing the analysis. So we're going to get out of this design. And here's a system that was sent in by a customer, an EasyPower user, that had both photovoltaic and a battery bank and was having issues. And in fact, I think I was talking to a group during a workshop that had a similar problem. And that is, this is fairly common as far as the orientation of my modeling, where I have a bank of batteries, all individually fused, going to my inverter. And if I go to short circuit focus and fault all the buses, we see that, let's see, for this bus down here, if I look at the Arc Flash Instant Energy, I've got 800 calories showing up, and that's with the 2-second maximum time. Now, the reason for that is, and at this point, I'm not talking about a hard and fast rule. I'm talking about common sense approach to what you're looking at. If we go back and double click this bus, sure enough, there's our 800 or 860 some odd calories. If I look at current, sure enough, the maximum current on this bus is 89,000 amps. That's because I got 7,000 amps coming from each battery on a fault. And sure enough, the battery itself, or the connect that we're showing in the one line, if I look at its instant energy, it's showing 246 calories because it's being hit with current from both sides. The fault from all the other branches plus the 7,000 amps that are coming from the battery. Well, the point I'm trying to make is this is an artifact of basically the way I've laid out my one-line diagram. And it's it's very much at the discretion of the designer or the engineer, but let me show what this looks like if we kind of redraw the situation. And when I say redraw, I'm going to move that fuse to the other side of the bus rather than on the battery side. And by so doing now, the fuse will protect the fault current coming from that particular battery. So now when I go to short circuit focus and I look at current, if I fault this bus, I still have the 80 some odd thousand amps, but that 6,000 amps now is going through the fuse, and the fuse will protect the bus, and conversely or inversely, the fuse will protect the battery from that upstream fault. So now when we're looking at instant energy and we fault this bus, now we have 6 calorie exposure as opposed to the 800 or 600 some odd before. Now again, this is still limiting it because we're talking about the DC current, but what the principle is each of these fuses will protect the main bus from a fault current being contributed from that individual battery. So anyway, it doesn't change the system itself. It does change the way I consider what the protection strategy is, both for the workers, because now working on this particular bus, my actual fault exposure or instant energy exposure is really something less than 8 calories. Now, just to kind of double check this, I'm going to look at my short circuit options, and we're looking at, in this case, let's go ahead and update it to the 2018 version, exclude the main, use integrated method. And I didn't limit the time there because I have on my individual bus calculated time. And I'm looking for my short circuit current. Okay, well, so that makes the point. Quite literally, the only difference between this system and the one we looked at a few minutes earlier is a location in the model of where this fuse is placed. So it doesn't matter as far as the simulation and power flow. It does matter on the way the calculations are made for bus protection. All right, so that's a word to the wise. Another thing I've found to be unusual is if we go to coordination, because coordination works in the DC range as well, and we fault an individual bus and look at it current and try to do sequence of events, what we get is I need to look at current, fault an individual bus, and look at sequence of events. What we get are all these fuses now tripping in 15 milliseconds, and they're all simultaneous as far as the current. And so that kind of proves the point. If I go back to the original drawing, let's look at short circuit current, fault the individual bus, and coordination, sorry. Now we can see that they don't trip, and that's quite literally just due, or they're not indicating that they're tripping because they're not upstream of the bus that we're talking about. Okay, so I beat that one into the ground. If you got any questions, by all means, let me know. Let me check to see if we got questions that are worth jumping on. Good enough. All right, so that concludes what I was wanting to cover today. By all means, I want you to check out the website for additional webinars or refreshers. And if you got questions about this, you're welcome to contact me or tech support at easypower.com. Thank you for attending today.